You're listening to the Knowledge Archives podcast. Welcome to the Knowledge Archives podcast. We're a group of students on a mission to learn from as many different disciplines of knowledge as possible. I'm your host, Madhav Malhotra, and today I'm lucky to be joined by Dr. Nishant Malik, Assistant Professor at the School of Mathematical Sciences at the Rochester Institute of Technology in the US. His work focuses on studying complex networks like the global climate with mathematical techniques, and this has let him understand problems like how climate change has affected past civilizations. I'm very much looking forward to learning more about this specialized research today. Now, one quick note for listeners before this conversation is that we do talk about many mathematical terms that I certainly did not know before this episode. So I have quickly defined a bunch of the key terms in the description or the notes of this podcast, and I'd highly advise people to check it out before listening to this episode. So thank you for joining me today, and I'm very much looking forward to hearing more about this unique discipline today. And just before we get started with all of the details, I'd love to hear a little bit about your story, an introduction to what you're working on, and how you got started with this area of work.
So my name is Nishant Malik, and I am an assistant professor at Rochester Institute of Technology in Rochester, New York. My area of research is complex systems and data science. I have some favorite tools which I use for my work. One of them is networks, then dynamical systems, a little bit of applied statistics. So these are the kind of tools I employ in my work. So I grew up in India, and then I did a master's in physics at University of Delhi. And then after that, I moved to Hyderabad, which is in South India, and I did a master's in computational techniques. Then I went to Germany to do a PhD at Potsdam Institute for Climate Impact Research. And that's where I got introduced to problems and issues in climate. After finishing my PhD, I moved to UNC Chapel Hill to the Department of Mathematics there, and I did my postdoc. And then after that, I went to Dartmouth College in New Hampshire, where I did another postdoc, and I was an instructor in applied and in computational mathematics there. After that, I got this position at Rochester Institute of Technology.
Yeah, it's very fascinating to hear about all of those different experiences, and I'm sure that has helped you in figuring out a more multidisciplinary perspective to look at these ideas through. And I know that at first, this entire field, complex systems, thinking about its real life context, it can be a bit bizarre. So, would you be able to give a bit of an introduction as to what complex systems really are?
So what I really mean by complex system is if you have a system which can be divided into two components. One, some kind of a dynamical unit, yeah, and two, some interaction between these units. Say, for example, human society, yeah. Human society has humans, and humans are dynamical units, and they're interacting with each other through relationships. Or maybe human brain, yeah. Brain has at the cellular level have neurons, and these neurons are connected with each other and they interact. Same you can say about the climate of the earth. Climate has different sub processes. Something is happening in the Pacific, it is connected with something going in the Indian Ocean. So there is this connectivity between processes and units. I use two words: a dynamical unit. It means that you might have to apply ideas from dynamical systems to understand what a dynamical unit is. And then I said interaction, and interactions mean that there is some kind of a network. So, for example, I was giving you the example of brain. In brain, you have neurons, which are highly dynamic cells, and they are interacting through this web of connections of axons. So it could be considered a network of these interacting dynamical units. So that's why I talked about dynamics and networks coming together in this stochastic. Processes comes into this picture because, say, for example, if you take brain, most of the phenomena at the cellular level is stochastic. Yeah. For example, when a neuron talks to another neuron, it talks through chemicals called neurotransmitters. And these neurotransmitters, because their concentration can jump up and down, so there is some level of stochasticity in that.
Mm-hmm. And what is extremely intriguing about all of these different examples is that if you think about it from the point of view of typical science, you'd imagine that you have a neuroscientist studying the brain or a meteorologist studying the climate. But when it comes to the mathematics of the situation, it transcends all that and links all of these areas together. So, from the perspective of math, how are these phenomena of complex systems linked together?
So it depends on at what level you are looking at a system. So, for example, if you want to see Earth and you want to model oceanic flows, yeah, then you probably will have to go into a discipline like fluid dynamics. The way I approach these things, when I claim to be complex systems, the ideas of complex system cannot give you all the answers to these problems. Yeah. For example, a neuron in itself is a complex system. Yeah, and you can analyze it at that level, and the mathematical methods that you will need to model a neuron would be very different than what you will use when you're trying to model these interactions. So it depends on what level you are trying to model something, and the mathematical methods depend on that. So it's not like some kind of a reductionist thing that you can answer every question from just using one toolbox.
Mm-hmm. And now, given the importance of not just sticking to one area of mathematics and being able to do real work in this field, what I thought would be very valuable would be to try to explore these areas in more detail, and maybe we can look at one type of problem that you might try to solve and apply all of these areas together in.
So for example, let's take the problem of this time series analysis and demise of a civilization. So one of the ideas is that some of the civilizational evolution and the human evolution has been driven by climate and past climate changes. Say, for example, there are theories that humans moved out of Africa because it became harder to live in Africa because of climate change. Such climate changes has happened in the past. They are not of similar nature or kind as we are seeing now, yeah, because we are seeing a climate change at a very rapid pace, but on a slower pace and enough of different nature altogether. So one of the ideas is that maybe the Indus Valley civilization also declined because of climate change. Now, if this is the hypothesis, how you can answer this? The only way to answer this hypothesis is to look into data into the past, yeah, some kind of paleoclimate data. Now, paleoclimate data is usually comes in form of a time series. So you will have two quantities, time and something representing, variation, some kind of a proxy representing a variation of a climatic parameter. It could be temperature, it could be rainfall. The data that I analyzed for this particular paper was a record that came from a speleothem. Speleothems are these growths that you have inside caves. So they are very good records of Earth's past climate. And what you can do is that you can take these speleothems from the caves and you can look for different levels, different concentration of different isotopes in these. And these isotopes records the temperature of the region where this cave is located. They also record, say, for example, the precipitation patterns and things like that. So I had a similar kind of a time series, which was a proxy of rainfall or hydroclimate, you can say generally. Now, the question is that if the climate has driven this civilization to its end, then this must be the signal for that must be in this particular time series, because this time series covered the period during which this civilization evolved into different phases. But the challenge is that paleoclimate time series are not easy to analyze. They're very challenging. And the challenges are the following. So first challenge is that because it's a proxy record, it's an indirect observation of some phenomena. So there is certain level of uncertainty inbuilt into it. The second is that these time series are usually short. They're not very high resolution, high temporal resolution. That is, you say, for example, now you can get a time series of every single second of a temperature at a particular spot on Earth. Yeah. Maybe not second, but at least a day long. Almost you can take any point on Earth and you probably will be able to access a time series representing the rainfall or temperature of a particular location. But this is not the case with paleoclimate time series. They have terrible resolutions and they also have uneven sampling. So sometimes the resolution, say for example, the sampling rate will change. Sometimes it was sampled 5 years at a time, then more than 5 years, then less than 5 years, and then there will be uncertainty within that as well. So there is so much uncertainty in it. There is uneven sampling in it, and on top of that, there is always noise, observational noise in it. So this is really crazy data, which is very hard to analyze. When mathematicians try to understand climate and different pieces of climate, we understand it as a dynamical system. And by dynamical system, I mean that we can write a differential equation. It could be a ODE or PD or whatnot of different phenomena that happens in climate. So for example, when you have these predictions that come on your phone, there is somewhere on the planet, some big fluid dynamics models are being sold to make these predictions. Now, most of our understanding about modern climate is based on this fluid dynamics and dynamical system kinds of ideas. But all these ideas are not exportable directly to a time series. The reason being that there we have equations, differential equations, and they can be solved and they can give this nice looking output, which we can analyze with our nice computers and things like that. But that's not the case there. We just don't have any equation, and we can't build these equations because our time series or our data is not so good. So one possibility is that you take present day model and then you run them into the past. You can run them into the past, but the problem is that there's a lot of uncertainty, because to run something in the past, you need initial conditions. And the initial conditions again will come from this same proxy data. So if the proxy data is not very good, it has all these problems, then your past models will also be problematic. So I took a different approach. I said, okay, let's say we have this time series. Let's analyze this time series and try to see what's inside. So one of the ideas in dynamical system is of dynamical transition, that when you have a system and it has some parameter, say, for example, monsoon, we know that monsoon is driven by the gradient between the land and the sea, the temperature gradient, because in the summer, land gets more heated than the sea. And so there is a temperature gradient, which in turn creates a pressure gradient, which makes moisture-laden wind from sea to blow towards the land. Now, on a longer time scale, hundreds of years or thousands of years or millions of years, we know that the Earth's insolation changes. And by insolation, I mean the amount of the sun, because Earth has different cyclicities. It has a tilt, which tilt changes. Then there are sunspot cycles on a shorter time scale. So there's a lot of different phenomena that happen because of the planetary motion that will change the amount of solar insolation that we receive. If that changes, that means this gradient that I was talking about will also be influenced by that. And as a result, the monsoon will be influenced by that. So we know that that's one of the parameters or one of the factors that will influence it. So assume that there is some hypothetical parameter which we don't know, or parameters which we don't know, which are changing. And these hypothetical parameters, if they are changing, if you're tuning them, then what can happen is that they can take a system from one kind of regime to a different regime. So many systems tend to show this kind of what we call bifurcations. Say, for example, system was stable and it became unstable. System was oscillating, then it became chaotic. So we have this one single time series. And the idea is that if monsoon has undergone this kind of a transition, that could lead to the end of the civilization. So let's analyze this time series. Now, how will we analyze this time series? One possibility is that you take this time series and do some kind of a geometric analysis. What I mean by geometric analysis is the following: that when you have, for example, let's say a differential equation. Differential equations are very hard to solve, okay? The differential equations that occur in real world. And because they're very hard to solve, what you will do is you will do a kind of a geometric analysis of these equations. By geometric analysis, I would mean that you will take it, you will put it on a computer, and computer will numerically solve it, and then you will plot it, and you will try to see that if I change parameters in this equation, how my solutions are changing, how the geometry of the solutions is changing, okay? Now, I do not have an equation. Can I do something similar with my time series? Something similar to what I would have done with my equation if I had an equation, okay? Now, the trick is that I do a similar kind of a geometric analysis. I assume that it comes from a dynamical system. I do not have a differential equation for it, but I can still try to do a geometric analysis. So what I do is through some jugglery, by using some of the modern methods from machine learning, I look for geometries hidden inside this time series, which we call manifolds. And I look if the structure of the manifold that's hidden inside it has a change over time. If it has changed, it means that there was a transition in it. So I can always develop a metric which can look at a geometric shape. If I give this metric different geometric shapes, it can tell me, hey, these two shapes are different. And I'm not talking about simple geometry. These are very complex structures that are hidden in this time series. And we have mathematical methods to extract those structures out of it. So what I'm telling you is that now what you are doing is that you're using all the methods that were developed for differential equations. You're applying these methods to a time series without having the equations. So you're skipping the part of equation. So all the ideas, you have pulled them up and you are applying them to a time series. And what we saw that indeed there were two hidden geometries in this time series, one representing the time when the civilization existed and the one after the civilization existed. So there were two different kind of geometries hidden inside this time series, which we were able to extract and see, yeah, really, there were two different monsoons. If you talk to paleoclimatologists who are experts on climate, they say that there was an aridification of this region because monsoon became weaker. So I was not interested in telling them, hey, monsoon became weaker or it became stronger. I was more interested in figuring out whether monsoon was different. Was there a dynamical transition in the system? So this is how you apply one problem. So there are so many things that goes into it, that a method developed for totally different context, you take them up and then you apply to this. Now, this problem is a problem in complex systems. These are complex systems that are high dimensional. There is no linearity in them. There are interactions between different things. Yeah, so these are kind of complex systems, but so there is no one recipe that, hey, take networks and it will work with every problem. It's problem specific. There is a problem, yeah, and then you define a problem, and then once you have understood that problem, then you try to bring in mathematics or a mathematical method to solve that. So that's how a lot of problems especially in physics and to some extent in applied mathematics are done. If you look at work of great physicists, say for example Newton or Einstein, you will see that that's what they did. They had a problem first, and then they tried to develop a mathematics to explain a particular phenomena. So that's what Newton did. Newton he knew about the planetary motion and he discovered gravity and all that. But when he wanted to explain to the world that how things work, he discovered calculus and dynamics. I mean, of course, if you are a pure mathematician, you are in a different way. You will have abstraction and you will be talking about abstract things.
So if I understand correctly, when you are thinking about your research, it's often that you're first of all looking at these phenomena that you're interested in explaining, and then you have a large individual role in determining, if I look at the data, I imagine these are the particular problems that we can think about in analyzing this. And as a result, I'm going to try to approach it in this unique way. And you have a large role in making those decisions and putting these fields together.
Yes, so a scientist, of course, has a role in that. So once you have this problem, what method will work on it, you don't know a priori. Yeah, you will try different tools, different ways of doing it, and there is also a tendency that you probably will use your favorite tool to solve the problem. So, for example, if you go and say meet a person from statistics, they will have their favorite tool. Hey, I will go and do some kind of Bayesian statistics or not. Yeah, if you go to a computer scientist, hey, I have this is called change point detection and anomaly detection. That's what I will use. And if you will come to a mathematician like me, I would say, hey, let's use dynamical system to solve this problem. So everybody has different tools and they have different strengths and limitations. And one has to understand what the strength and the limitation of your method is. And also the methods that you have doesn't apply to every problem, but there are certain problems where they apply really well. That's why you will see that scientists are specialized in something. Say there could be a mathematical biologist working on just neurons, just modeling the electrical activity. There could be a mathematical biologist who's just working on the heart, doing cardiac modeling.
Yeah, I think that's very fascinating because especially earlier in mathematics education, it's always like there's one right answer and you always have this particular approach, but it's really interesting to see how different the world of applied mathematics is in being able to combine these areas together. And I very much appreciated your explanation of that one particular problem. I know we won't be able to do that for all the problems you look at, but if you were to outline some of the other areas, what are some other problems that you might solve in this context?
So there are some problems that my students are working on. Yeah. So there is this one interesting problem that we thought about with networks. Say, for example, in predicting monsoon. Yeah. Now we know that there are certain atmospheric phenomena or patterns in the atmosphere that can give you insight into monsoon, or there are patterns which are of predictive value. Say, for example, if there is an ENSO in the Pacific, you know that it will affect monsoon in a certain way. So there are these patterns spread over all over the planet that affects monsoon and monsoonal rainfall. Now you can use this fact to make prediction. Okay, a priori you don't know what these patterns are, but there are a bunch of these patterns spread all over the planet. So what we did, we took climate data from last 60 years and we turned this climate data into graphs, into networks. And how we did, so this data comes from NOAA and it's a reanalysis data. What it means is that what they have done is that they have divided the whole Earth into rectangular grids. And at each grid, they have a time series, say, for example, of temperature at certain height. Yeah. And you take this time series, at these different locations, and you calculate a correlation between different time series. Yeah. And if the correlation is above a certain threshold, you say these 2 points on the planet Earth are connected. So now what you have done, you have taken this whole very large data set and you have converted into this connections and nodes and things like that. So you have encoded your patterns into the network. Now what you can do is you can analyze these networks and look at the structure of the network, say what kind of a structure I had in the month of May of some year, and use that particular pattern in the network to make a prediction. So this is one of the things that we have recently done, to turn the data, the large scale data, into networks, and then look specifically and very closely into the network structure and evolution of these network structure to make predictions of monsoonal rainfall. Now, the way we these days predict monsoon, these are very expensive calculations. There are these large supercomputers on which you solve this gigantic set of equations, and these huge models that you will be using hundreds of people to do those kind of simulations. But the way I'm describing you is very simple. So these are very low complexity algorithms which can make a prediction about monsoon. So that's another thing that we are trying to develop. So what I call this area is developing low complexity data driven models for understanding and prediction of climate.
That's very fascinating to hear about. I think it's just becoming more and more clear how these particular approaches, you can apply them to so many contexts, and just the sheer real world utility of that. And that brings me to one of the areas that I wanted to wrap up this conversation with, which was around the real world. Because obviously, you described how when we're picking and choosing between these different networks, we have all these uncertainties, we have all these assumptions. So, from your perspective, could you walk us through some of the largest assumptions that you think people use when it comes to these types of problems?
So I would not be able to say it in behalf of everyone. I can tell you about my assumption. Take the first problem about a time series. Yeah, I am assuming that this time series comes from a dynamical system, and I am assuming that this dynamical system is perhaps deterministic in some sense. It may not be. That's one assumption that goes into my first method. This is a good assumption because we know the modern monsoon is very much a dynamical system and it has deterministic properties to it. The second project I can talk about, that when we are calculating correlations and converting into networks, we are talking about linear correlations. Yeah. And on the planet Earth, this is a very, very big assumption because things are not linearly correlated. There are more complex kind of correlation between climate phenomena happening in different parts of the world, or different locations. So, but you will have to always make some assumption because there has to be a starting point. And assumptions are very important because you are trying to simplify a model, or you're trying to simplify your analysis. Unless you do that, then there are so many things that you will keep adding up and things will become more and more and more complex, and which you may not be able to neither understand nor analyze.
Definitely. And then finally, the last question I had for you was that if you think about the future of how research is evolving in this discipline, what do you think are some of the largest underexplored areas or areas where you see gaps in the research that is coming out?
So my understanding at the moment is that the most fascinating things at the moment are happening in the world of what we call data science. And the reason being that nowadays we have gigantic amount of data about almost every phenomena. So for example, an interesting example that I keep giving people, let's take cars. Yeah. Cars 20 years back didn't had these sensors in them. Yeah. they couldn't tell that there is something wrong with the pump somewhere in your engine, yeah, or some particular thing is off, or the tire pressure is low. But now you see that you have this computer fitted into your car and all these sensors everywhere. So how is it that happening? That's happening that you have these very powerful sensors. Then combined with it, you have this computational power. You have these little things. You can really miniaturize very massive computational machines these days. Your phone, for example, yeah, your phone collects so much data about human behavior. So we have all this data that's coming from these modern sensors and technologies. And also at the same time, we are having a growth in computational power. We are having growth in the storage capacity and things like that. And what it has done is that it has opened up a new era of modeling, and this era is basically era of data driven modeling, that you have this giant data, analyze, look for pattern in this data, make sense out of this data, and then make predictions. And this is what machine learning is all about. So that's what I think is the most upcoming area, or where the most important discoveries of our times are going to happen.
And finally, if anyone is curious to learn more about these ideas and your work, where might they go?
They can just Google me, yeah, and that's one way to find me. They can also write me an email, and I can give them some resources.
All right, that sounds great. Yes, I'm sure anyone who's curious can learn more there. And I really wanted to thank you again for taking the time to record this podcast. I know that sometimes it can be a little bit challenging to explain these complicated ideas in a simple way, but I really appreciated your help with this today.
Thank you, Madhav. Thank you very much. Thanks for the invitation, and thanks for talking to me.